Good afternoon. We will begin today another lesson on techniques of integration, the so-called trigonometric integrals. And this is another lesson that you should probably cover it in two settings at least. I would typically take 2 class times if I were to teach this in a traditional setting. Remember, this is not a requirement, it's just not a good idea to go over the whole thing unless you actually already have the energy and time to put twice the amount of work you would put in a regular classroom. And as a rule of thumb, let me remind you again that if for a duration of a video about 25-30 minutes, you should probably count 15 minutes of you sitting down and actually taking the notes and following the lecture. Because I go a little bit faster on the video and I don't take breaks. So if this ends up being, for example, 50-60 minutes, then it's a good idea to take to go over it in 2 instances of 50 minutes each, unless again you really want to sit for 2 hours. This is not because the topic in this particular case, not because the topic is overly difficult, but because there are different cases that I'd like to cover and different type of relevant examples that I would like to go over to complete the whole picture of what we're supposed to talk about. In fact, from a strictly mathematical strategy point of view, the lesson is not at all difficult. It's basically an application of the U substitution, except that the U substitution is applied in this case to integrals involving the most usual trigonometric functions like sine, cosine, tangent, cotangent, and so on. Primarily sine and cosine are the ones that you will encounter more often. And before we proceed, please write down these 3 formulas. They are actually related. The first one probably most of you know already, right? The fact that sine squared plus cosine squared x equals 1. The same identity can be written in terms of tangent secant or cotangent cosecant. So if I were to divide this first identity by cosine squared, and remembering that 1 over cosine is secant, you get an analogous identity in terms of tangent and secant squared. So 1 plus tangent squared is secant squared, 1 plus cotangent squared is cosecant squared. The third one is obtained by dividing the whole identity, the first one by sine of x. You don't have to memorize this, though the first one is probably known by most of you. Just make sure you have it in front of you because we're going to use these formulas repeatedly. Let's also remember the basic derivatives involving sine, cosine, tangent, and cotangent. So the derivative of sine is cosine of x. The derivative of cosine of x is minus sine of x. Then we have the derivative of tangent of x equals secant squared of x. And then finally the derivative of the cotangent of x. We need the derivative of secant for the purposes of this lesson. So the derivative of secant x is secant tangent, sec x tangent of x. So all of these trigonometric integrals that we learn will basically involve the application of these formulas and these derivatives to come up with a U substitution that allows us to solve. We basically arrive to 4 techniques that can be applied to 4 types of problems, essentially. So pretty much like a formula, if you want, or a strategy to a more general type of problem. But before we provide these 4 different strategies that I talked about, let's actually get down to business right away by following 2 typical examples that you will encounter in this section, because we already know actually the theory behind everything we need to use to solve these problems. It's just a matter of essentially learning the strategy. So let's look at the first example, and let's say I want to find the antiderivative of sine squared x cosine third x, and I want you to pay attention to the powers of sine and cosine, because we will learn how to integrate any function of this type, basically sine raised to a power multiplied by cosine raised to another power, a natural number power, basically. So it may not be obvious how you can use U substitution, but in combinations with the formulas that we have here in the right corner and with some little algebra tricks, we can actually do this U substitution. And let me remind you that the U substitution means that I need to write the function to integrate in the form of the composition of two functions multiplied by the derivative of the inner function, if you want. So I need to see this basically a function of a function multiplied by the derivative of that inner function. And here's how we can achieve this. And in this combination, the key thing is the fact that the power of cosine is odd. So the power of cosine is odd. This will be important, which for the reason I hope you will see as we move along with the exercise. So let's save one factor of cosine separately. So basically I have cosine to the power 3x. Let's take a cosine of x separately. And of course the remaining power of cosine is 2. Right? So you simply break down cosine third into the product of cosine squared x times cosine of x. I call this saving a cosine factor separately, and then of course writing the remaining power that was there. Obviously, if it was cosine to the fifth, for instance, then you would say cosine fourth x times cosine of x. So let's save this cosine of x dx. And now you should think about the U substitution for sine of x. And the problem with the remaining cosine squared, because it's cosine squared, and more generally because the power of cosine, the remaining cosine, is even, then I could use this identity, the first identity, to write everything in terms of sine of x. So basically, if cosine of x dx will play the role of g prime of x dx, where g of x is sine of x, the whole thing will work for this U substitution if I can write the remaining part of the function to integrate in terms of sine of x. And I could do this provided that the power of cosine is even. So from the identity, I can write cosine squared 1 minus sine squared, and I can plug it into the function to integrate. So instead of cosine squared, I write 1 minus sine squared, and then cosine x dx. So let's pause for a moment. Let's not rush to actually understand how the trick worked from the beginning to the end. I hope now everybody sees this as a U substitution. So a composition of two functions in which the inner function is g of x equals sine of x. So this will be basically my U substitution. U equals sine of x. All right, why this worked in the first place? Because it doesn't work for all combinations of powers. It worked precisely because the power of cosine was odd. Because we needed a cosine to play the role of g prime of x. So cosine of x is the derivative of sine. And I need the remaining power of cosine to be even, because only for even powers I could use this substitution and write everything in terms of cosine. It will work with other powers as long as they are even, as you will see in another example right away. So from this point on, we proceed with the U substitution. So if U equals sine of x du is cosine of x dx. And now the integral becomes a polynomial. So sine squared becomes u squared. 1 minus sine squared is 1 minus u squared. Cosine of x dx becomes du. We may have to do some algebra still further, but in the end it's just the integration of a polynomial. So then it's going to be just a power rule. 1/3 to the power u to the power 3 minus 1/5 u to the 5th. And now, of course, come back to the original variable. So u3 sine of x to the power 3 minus 1/5 sine of x to the power 5 plus a constant c. So you can pause for a moment, and you should pause to gather your thoughts and rework the exercise and see how these steps worked out. And assuming you just did that, let's move on immediately with another similar example to emphasize why any odd power will work in this combination. So suppose, for example, that I have sine squared x cosine fifth x dx. Oops, cosine fifth x dx. I made a really ugly x here. The same idea works, right? I mean, again, we anticipate, because the power of cosine is odd, we anticipate the substitution u equals sine of x will eventually work. And to do that substitution, we save a cosine of x separately in anticipation that this will be my du. And the remaining power of cosine is even. Now pay attention here, the identity that gives me cosine in terms of sine is for cosine squared of x. So here I'm going to replace cosine squared, so I can write cosine fourth as cosine squared x, again to the power 2. And then, just like in the previous exercise, we're going to replace cosine squared with 1 minus sine squared of x. And just like before, now you have your composition of functions, in which again the inner function is sine of x, that's your gx basically, and g prime of x. So that's your u substitution. Now, because you have higher powers than in the previous example, obviously you will have more algebra to perform. So once you do the substitution, so u equals sine of x, du again is cosine of x dx. So we're going to end up with u squared 1 minus u squared quantity squared du. So now I have to do more algebra here. So when I raise this to the power 2, that's 1 minus 2 u squared plus u to the power 4 du. And then I'm gonna distribute. So it's gonna be u squared minus 2 u to the power 4 plus u to the power 6 du. And then finally integrate. 1/3 u third, 2 over 5 u to the power 5 plus 1 over 7 u to the power 7. And then finally go back to the original variable. So replace back u with sine of x. So I want to basically anticipate that although we're going to have plenty more examples with other types of combinations, this is essentially the whole idea. Via a trigonometric identity and via some combinations of powers of these trigonometric functions, we could essentially use the u substitution. This is nothing but a fancier application of the u substitution when it deals with trigonometric integrals. And let's move on with another example before we state this as a rule, because we can basically provide these techniques, like I said before, as rules. Basically the same idea, the same combination of cosine and sine, but in which sine has an odd power. And I want you to think about, before we move to the second page, what would you do if we have essentially the odd power switch to the sine power? So what would you do, for instance, if you want to integrate cosine squared x sine third x? So I actually encourage you to pause for a moment and see if you can figure out the trick. Because it's the same idea, except you have essentially different substitutions. See if you could do this on your own, and then check with me as we move on to the second page. So stay tuned. Okay, so I hope that you figure out that everything is in reverse now. I mean, not in reverse. What I mean is that the whole game works, except that now it will work if you substitute u for cosine of x. and then remembering that du is minus sine of x dx. So now this trick works because sine of x has an odd power. Why is that important? Because of the same reason as before. One can actually take out a sine of x dx, or save a factor of sine. Don't worry about the minus for now. Remember, we can always move the minus to the du. We could do that when we do the substitution. So save a sine of x dx, save a factor of sine and attach it to dx in anticipation for this u substitution, and then write the remaining power of sine, which ought to be an even power, just like before. So because it was sine third in the beginning, now by saving a factor of sine separately, then you're left with sine squared of x. And we're going to use the same identity here in the corner, but by replacing this time around sine squared with 1 minus cosine squared, because the idea is to write everything in terms of cosine of x. So now my integral becomes the integral of cosine squared of x times 1 minus cosine squared, and then sine of x dx. Okay, so now let's write down the u substitution actually. So u equals cosine of x, du equals minus sine of x dx, and of course minus du, I gotta move the minus over, is sine of x dx. All right, so now my integral in terms of u becomes u squared, quantity 1 minus u squared, and sine of x dx minus du. Don't forget to, don't lose that minus that comes from the u substitution. And so when I expand this with the minus here from the u, becomes minus u squared plus u to the fourth. And then finally, power rule. And yeah, let's finish it here. Equals minus 1/3 cosine third x plus 1/5 cosine fifth x plus a constant c. Okay, so before I actually state this, what you do as a rule essentially, well, actually, let's do the rule right now, and then I'm gonna add another example involving sine and cosine. So how would you state this as a as a rule, as a procedure, basically? So if you have a combination like this, the integral. So let's say let's write it down as a strategy. I don't want to call it theorem or anything like that. So if I have to integrate, let's do my first example, the one that is similar to my first example, right? We had the odd power of cosine. So if I have to integrate sine to m to the power mx times cosine to the power 2n plus 1x dx, so that would indicate an odd power of cosine, then the strategy is to break down the cosine by saving a cosine x separately, replacing cosine squared, so this is basically cosine squared x to the power n, right? It's an even power remaining once you move a cosine separately. Replace cosine squared with 1 minus sine squared, and then what you'll have here in the end is suitable to a u substitution by making u equals sine of x. And then you continue from here. So that's one aspect of the strategy, and then corresponding to the second example, strategy 1, strategy 2, that's the other way around. Let's say you have cosine to the power mx and then sine to an odd power to the power 2n plus 1 x dx. So you have an odd power of sine of x. Then in this case, the strategy calls for saving a sine of x separately. So there you're left with sine of x to the power 2n. And then you're gonna, and this is essentially sine squared to the power n. And then you're gonna replace sine squared with 1 minus cosine squared of x to the power n sine of x dx. And then you proceed with u substitution by replacing u with cosine of x. Du will be minus sine of x dx. Don't forget to move the minus to the left, and then you proceed with that u substitution. Okay, so you may wonder now, what if both are odd? Well, in that case, you're in luck. You could use either of the two methods, although be prepared for the fact that the answer may look different, although it's correct either way. So let me do it here. This will be my, let's see, my fourth example. Just for fun, I'm going to do this example both ways, because it's important to realize that in these situations, when you actually have a choice between strategy 1 or 2, it doesn't matter which one you choose, but be prepared that your answer may look different than in the back of the book, depending on the how what was the approach on that book essentially. Okay, so say you have the integral of sine of x cosine third x. I can use either strategy 1 or strategy 2. Actually, the easiest one is to use strategy 2 because you already have sine separated and cosine, right? So if I use strategy 2 and I have to save a sine of x separately with dx, it's already there in this format. So notice there's no, because there is no extra sign, I don't need to use the identity anymore. Sine squared equals 1 minus cosine squared. I don't need to do that. I can simply proceed with replacing u with cosine. D is minus sine of x dx. And this becomes essentially u third minus du, because you move the minus over once again. And then that becomes minus 1/4 u to the power 4, which is minus 1/4 a cosine to the power 4x plus a constant c. All right, so what if you want to use strategy 1 and you say, okay, I'm going to use strategy 1, so I'm going to keep the sign here, I'm going to save a cosine of x separately, I'm going to use the identity for cosine squared, and then I'm going to use the u substitution with sine of x. So then this becomes u quantity 1 minus u squared du integrate, and then the final answer would be 1/2 the sine squared of x minus 1/4 sine fourth of x plus a constant c. So I know it may look strange until you get a little bit experienced with this and you have a little practice, but really these two answers cover the same. I mean, they are the same. They give you the same family of antiderivatives. I'm a little bit fancier with the language here because remember, there's no such thing as a single antiderivative. because of that arbitrary constant c. But they cover the same family. The problem with trigonometric functions is that because there are so many trigonometric identities in which you can write functions in terms of other trig functions, often the same answer can look quite differently. So, I mean, it's one of those situations in which you have to make sure that you check your answer. The easiest way is to put these two, I'll show you when we go over some technology. Put these two together in, let's say, in a computer algebra system, and the computer algebra system should be able to tell you that they are equal indeed. I can show you actually with some computation here why they are indeed the same. So y minus 1/4 cosine to the fourth is actually the same as 1/2 sine squared minus 1/4 sine fourth. Again, bearing in mind that we have this arbitrary constant. Well, take a look at this. If I take the first version, let's say, I hope I have enough room here just for fun. You don't actually have to write this down in the notes, but just follow me a little bit. If I take the first version of the answer, minus 1/4 cosine fourth plus a constant, and I actually replace again cosine squared with 1 minus sine squared. So it's going to be 1 minus sine squared squared, right? Because I replace sine squared. And I do this messy algebra. So I expand the parentheses, so that's going to be 1 minus 2 sine squared plus sine fourth plus c. And if I distribute minus 1/4, then it's going to be plus 1/2 sine squared, and I hope you recognize it from the second answer, minus 1/4 sine fourth plus c. And so notice that I obtain 1/2 sine squared minus 1/4 sine fourth, and this minus 1/4 can be combined with the arbitrary constant and renamed plus c. It's something you will do often when you take differential equations. So since c is an arbitrary constant, you can basically blend in minus 1/4 plus c and make it another plus c, or plus c here in the second version of the answer. So they cover the same family of antiderivatives. That's the important take-home message. So at this point, if you're not up to cover the same thing in one setting, you can basically move on with the remaining part of the lecture in a different setting. But to conclude, when we have sine and cosine in which one of them, at least one of them, has an odd power, then the strategy is to basically take that odd power, save a factor of it, and then rewrite everything else in terms of the other trig function. So if it was cosine to the power with one odd power, eventually you will have a u substitution with sine of x. And you move on with that strategy as shown in the examples. So on the next page, let's see what do we do if we have only even powers. That'll be the last, not for the lesson, but that'll be basically the remaining case that I'd like to cover involving sine and cosine. For tangents and secant, so I'm going to cover also secant and tangent, and I'm going to skip the whole version with cotangent because then it's going to be too long, but same idea would work if you have combinations of cotangent and cosecant. So next on the plate is what do we do if we have only even powers of sine and cosine? So how do we handle the even only powers of sine and cosine? Well, to the rescue, we have two extra formulas which are called half angle formulas or double angle formulas. There are different versions of how to write these formulas, but for the purpose of our lesson, I'm going to write them down in a way which is suitable to algebra that we need to perform after that. So sine squared of x can be written as, is equal to 1/2 quantity 1 minus cosine of 2x, and cosine squared x is equal to 1/2 times 1 plus cosine of 2x. Again, you don't have to memorize these, just write them down. These are called half angle because another versions of how they're given is, let's see, to write cosine of 2x either as 2 cosine squared x minus 1. That's essentially identical to this second one that I wrote here on the left panel. Or cosine of 2x is 1 minus 2 sine squared of x. So you will see these formulas given like that, but for our purposes, for the purpose of how we use them to integrate even powers of sine and cosine, this is the format here. These are identical formulas again, it's just a matter of how you write what you write on the left side, either the cosine squared or sine squared or cosine of 2x. Okay, why they are important for our purposes? Notice that these formulas allow you, so let's actually write it as a remark. These formulas allow you actually, right? It's a plural. So these formulas allow you to reduce the power of an even power of sine and cosine. So basically, by applying these formulas repeatedly if necessary, you can end up to a situation that you know how to integrate. So I'm going to focus, the algebra can be a little bit tedious, so I'm not going to focus on too many examples here, but I'm going to really focus on the three examples that occur more often in practice in calculus. Integrating sine squared and cosine squared. So if I have to integrate sine squared of x, U substitution doesn't work because we don't have an odd power. We can save a sign and then use the identity to replace the remaining one. So always remember that, because sometimes people keep on thinking about the U substitution and in the format that we had before, and they get stuck with this thing, you know, because if you save a sign, you're left with an odd power of sign. So you can't use the identity before. The identity before only works for even powers of sine and cosine, right? Because we have sine squared plus cosine squared equals 1. So if I have an even power, again, use the double angle formula, or you can call it the power reduction formula if you want. And notice in both, whether you have sine squared or cosine squared, you end up basically in terms of cosine of 2x. So sine squared of x is replaced by 1/2 1 minus cosine of 2x. And now to integrate, of course, you need to distribute the constant and integrate basically each term, because this is basically the summation of two functions. And you do have a U substitution, but at this point, it's highly recommended to do this U substitution in your mind. Remember, it's like the backward chain rule. So the first one is immediate. The integral of 1/2 dx is 1/2 times x, so it's x over 2. And the other one, the integral of cosine of 2x, is 1/2 sine of 2x. So there is a 1/2 from before, and then obviously another 1/2 sine of 2x plus a constancy. So in the end is x over 2 minus 1/4 sine of 2x plus a constancy. Make sure here, so cosine of 2x, yeah. All right, same manner for cosine squared of x. Cosine squared, again, via the same formula, is going to be equal to 1/2 1 plus cosine of 2x. And again, we distribute 1/2. Integrate term by term, so that's going to be x over 2 plus now 1/2 and another 1/2 becomes 1/4 sine of 2x plus a constancy. So the strategy can be basically expanded to any combination of even powers, except that again the algebra can be messy. So my next example, I'm not sure I'm going to finish it. Maybe I will. Let's see if I have enough room here. But I want to point out that I will avoid these type of examples in exams or quiz even, obviously, right? Because they take too much time. But it's important to know what you should do essentially if you're faced with this and you have to figure out by hand how to do this integral. So what if I have, let's say, combination of sine squared of x, cosine fourth of x? And I should say that before I continue, that sometimes there are different ways to go about, because there are yet other formulas, but I don't want to get too deeply on this. Again, remember, if you're faced with even powers, the idea is to reduce these powers via these formulas primarily, the ones that I just mentioned here with on the top of the page, to reduce the power. So sine squared is replaced by, let's say, 1/2 1 minus cosine of 2x. Here I have cosine fourth, so I can write it as cosine squared. So the cosine squared itself again is 1/2 1 plus cosine of 2x, again to the power 2. You're going to have 1/2 3 times that you can pull out, so 1/2 to the power 2 is 1/4, and another 1/2 that makes it 1/8. You can take it out, and now you just have to basically do some algebra and then see what you have after you simplify it a little bit. So you say it's rather tedious, right? I mean, let's do one more step. I can expand 1 plus cosine of 2x, so that becomes 1 plus 2 cosine of 2x plus cosine squared of 2x. And as bad as it looks, all I have to do is, I mean, there's nothing else I could do except expand it even further. So basically multiply term by term. So that's going to be 1 times 1 plus 2 cosine 2x plus cosine squared 2x, then minus cosine 2x times 1 minus 2 cosine squared 2x, and then minus cosine third 2x dx, right? So let's write it on the left, clean up a little bit. So it's going to be 1, see, 2 cosine of 2x with minus cosine of 2x becomes cosine of 2x. Cosine squared minus 2 cosine squared 2x, that becomes minus cosine squared 2x. And then finally minus cosine third 2x. Okay, so now how do we integrate term by term? Well, the first one is the immediate. The integral of 1 is going to be x. The second one is immediate. The middle term is what we did before. We can take it separately. And we apply the same strategy as for cosine squared x. Again, a reduction formula again. So this time around, if you pay attention, I'm going to use the same formula here on the top of the page for cosine squared x. But instead of x, I have 2x now. The important thing is to reduce the power, right? So this becomes now 1/2 1 plus cosine 4x now dx. And now it can be further broken down into the integral of 1/2 plus the integral of 1/2 cosine of 4x. And finally that's x over 2, 1 over 2, and then 1 over 4 sine of 4x. So that's it, just the middle term. As you can see, it's rather tedious, so we don't do this by hand too often, but that's the idea. Basically, you reduce the power until you break it down to pieces you know how to integrate by other techniques. I'm not going to finish the last step here, but cosine third 2x, well, this will be in the same manner. First of all, you can make a quick U substitution if you don't like 2x, but you don't need to do that. But this basically is an odd power of cosine, so this can work with the technique we learned before. Save a cosine factor. And you're going to write cosine squared 2x as 1 minus sine squared 2x. And it will work out by making the substitution u equals sine of 2x, du equals 2 cosine of 2x dx, and of course move the 2 over and so on. So notice the technique we learned can work if you have cosine of 2x, right? I mean, you don't need to have just cosine of x. It can be a constant times x. I mean, the technique is the same essentially, as long as you have an odd power of x. So I would say that when you have a combination of even powers of sine and cosine, in particular, be sure that you can integrate just sine squared or just cosine squared, you know, these two, because these two appear more often in practice. So with that, we're going to move on to the next page and see how we can handle same type of fun I hope you're having fun already. For secant and tangent. So stay tuned. All right, so this time around, we're going to start with the strategies and then finish with examples, because I hope by this point you kind of get the hang of it, right? It's just another U substitution, but now involving secant and tangent. With secant and tangent, sometimes things are a little bit harder to see, especially the last version I'm going to show you. But let's emphasize the formulas that will be relevant for our examples. So the identity is 1 plus tangent squared equals secant squared. And we can use it in both directions, either to get tangent in terms of secant or secant in terms of tangent. So in some applications, we're going to use this identity by replacing tangent squared as secant squared minus 1. Right? So the same identity can be used in both directions. And then, of course, the derivative rules for tangent. Tangent prime is secant squared. Let's see if it's here. And then secant squared, excuse me, secant prime, secant, the derivative of secant x is secant tangent. So the first strategy, I mean the first one for tangent and secant, in our counting, that's going to be strategy, I guess, 3. I didn't actually number the strategy for the even powers of sine and cosine, but that's fine. So strategy 3 is if you have an even power of secant, and then tangent power doesn't matter. So basically, if you have the integral of tangent to some power of x and secant to an even power, which I'm going to write it as 2n x dx. Here again, as you could probably anticipate, we're exploiting again the derivative of tangents. We anticipate to make the substitution u equals tangent. For that reason, the strategy calls that you save a power of 2 of secant, so you save a secant squared separately. So you're left with 2n minus 2 in the power of secant. Because this allows you, so now the remaining power of secant can be written as secant squared to n minus 1, basically, whatever the power is left there. And by doing so, you can use the identity in the first format to replace secant squared in terms of tangent. So you have your initial power, the initial term, tangent to the power mx. Secant squared is replaced by 1 plus tangent squared. And then times to, to the power whatever is left there in the power. And secant squared x dx. So this will be your du if you make the substitution u equals tangent of x. So basically you're left to integrate a polynomial like before, u to the m 1 plus u squared to the n minus 1 du, and then you proceed from here. And let's do an example right away. Let's see which example. We're going to do the integral of tangent of x secant fourth x dx. Okay, so save a secant squared. So you're left with another secant squared. Use the identity. Secant squared is 1 plus tangent squared. And perform the u substitution for tangent. And then you're left with u 1 plus u squared du. Distribute, integrate, and replace u back with tangent. tangent squared plus 1/4 tangent fourth plus a constant c. Okay, so finally the last one that I want to cover, the last strategy, is the one that has an odd tangent power. So basically the example that I showed you before can be done with this other strategy. So the strategy 4, when you have an odd power of tangent of x, and then the power of secant doesn't matter in this strategy. So let's see how we can emphasize this. So let's say you have secant to any power you like, secant to the power m, but tangent is raised to the power 2n plus 1, an odd number. So this strategy basically seeks to make the substitution u equals secant x. So I want you to focus on this top of the page and notice that if I anticipate to make the substitution u equals secant, so if I want to make u equals secant x, du is secant tangent. So here, this is the trickiest type of case, right? Here you need to basically isolate a secant tangent together with dx. So, and then the goal, of course, is to end up with an even power of tangent. So I can use the identity and replace tangent squared with secant squared minus 1. So here, again, we're going to take a secant tangent separately, and notice that in this case, the remaining power of secant will be m minus 1 if I pull the secant out of it. The remaining power of tangent will be 2n, which is even, and that's important. And then secant x tangent x will become later my du via this substitution. So remember, again, tangent to the power 2n, it's like tangent squared to the power n, quantity to the power n. Now I apply the identity by replacing everything in terms of secant. Oops. So I meant secant to the power m minus 1 x. Then tangent squared is secant squared minus 1, and then to n, whatever the remaining power is, and then secant x tangent x dx. So now I perform the u substitution that I mentioned here, and this becomes u to the power m minus 1, u squared minus to the power n du, and this becomes again a polynomial that I know how to integrate. So lastly, let's do an example that cannot be used either way, because see the example that I made before here, in fact, we'll do that probably on the second page, because the example that I made before can be used with strategy 4 as well. So actually let's do that right now, and then I'm going to finish the lecture with another page with 2 examples that can only work for either strategy 3 or 4, but not both. This one works for both, right? Because since I have an odd power of tangent, instead of making the substitution u equals tangent, I can go by strategy 4. So again, I can take separately, let's do this, the same example. So save a secant tangent separately, so I'm left with secant third x, secant third x, and then tangent x secant x, or secant tangent is the same thing. And now make the substitutions u equals secant x, du is secant x tangent x. So actually it's faster this way, as you noticed, probably. And this becomes now u third du, 1/4 u to the 4, and then of course in the end that's 1/4 secant 4th x plus a constant c. I know it looks strange, but 1/4 secant 4 plus c plus a constant c is really equivalent to the previous answer for the same problem, because again we have this identity, trigonometric identities, right? If I were to replace again tangent square with secant square minus 1, everything will boil down to the second format of the answer, depending on which strategy you used. So it's important actually when you have the option to choose the easier one or the faster one. So let's finish with the last part with 3 examples involving secant and tangent, but in which only one of the strategy works. So stay tuned for the last part. Alright, so let's do an even secant case, but in which tangent power is not odd, so that I cannot use the other strategy. So let's say I want to integrate tangent squared x, secant squared x dx. That's probably too easy, but okay, we'll move on with that. Tangent squared, secant squared, that's fine. Trying to think if it's make it a little bit more complicated, but I guess that's not. Well, let's make it actually secant fourth, so that it's not that trivial. Because, you know, with secant squared, there's nothing there, you don't need to use the identity. So let's say tangent squared secant fourth. And speaking of the identity, remember the identity we use here is 1 plus tangent squared is secant squared. If your goal is to make u substitution with tangent, or tangent squared x equals secant squared minus 1, if your goal is to make u equals secant x substitution. So with the even secant, your goal is eventually to get everything in terms of tangent except du. So that's your goal. So that means you save a secant squared, then the identity for the remaining part. So it's going to be 1 plus tangent squared. And actually, just for fun, because we didn't actually have a definite integral. So sorry, I'm making this modification because I just want to cover all bases. Let's actually make it a definite integral, and let's make some really nice bounds for this problem. So let's say it's 0 pi over 4. So because remember, the work, if you have a definite integral, shouldn't be that much different. The only thing is to keep track of the bounds and plug them in when you're done, when you find the integral. And when you make substitutions, remember my strong advice is to change the integration bounds right away. Okay, so we have tangent squared, secant squared is 1 plus tangent squared, the secant squared x will be du, right? So now we make the substitution, so u equals tangent of x, du is secant squared x dx, and let's write the new integration bounds. So if x is 0, u is tangent of 0, which is 0. If you don't remember that, use the calculator or draw a trigonometric circle quickly. And pi over 4 is the nicest number for tangent. Tangent of pi over 4, which is 45 degrees, that's 1. All right, so then my new integral now is from 0 to 1, u squared 1 plus u squared du. All right, so now integrate 1/3 u third plus 1/4 u fourth between 0 and 1. Now because we changed the integration bounds, we don't need to go back to the original, to the tangent of x, right? So that's going to be 1/3 1 to the 3 plus 1/4 1 to the 4th, and then minus 0 plus 0, which is just 0. So that's 1/3 plus 1/4. That ends up being 7 over 12. Okay, so this works with strategy 1, right? Because the power of tangent is not odd, right? So let's do an example now in which the power of tangent is odd, but the power of secant is not even, so that I cannot use the previous strategy. So let's say I have secant fifth x tangent third x dx. Okay, so in this case, the only way to go about is to make the substitution u equals secant x. And that means you need to save separately the derivative of secant, which is secant tangent. So you pull a secant and a tangent from these powers and make sure you write correctly the remaining power. So you're left with secant fourth, you're left with tangent squared, and then, as I said, secant x, tangent x, together with dx in preparation for this substitution. So this is going to be your du. Everything else should be in terms of secant x. So that means we're going to use the identity, the second version of the identity, and replace tangent squared with secant squared minus 1. So now my integral is secant fourth x secant squared x minus 1 secant x tangent x dx. And now finally we perform the substitution. So this becomes u fourth u squared minus 1 du. Distribute. And some power rules. And then finally replace u with secant. Plus a constant c. Alright, so remember to practice as soon as possible, especially with sine and cosine, which again, these are more often encountered in problems. And make really sure to not move on until you really understand the whole lecture. Because the next one, which it's called Trigonometric Substitutions, another very useful technique, which we'll cover, actually depends on this lesson. We will basically have trigonometric integrals as one of the steps, essentially, in the technique we're going to use in the following lecture. And that's it for today.